Let's wait till 2:05. Has anyone started on homework 0 yet? I know Chase has. I don't think he's here. So everyone, so please join Piazza at your earliest convenience, because I am very certain that you will run into issues working on homework 0. And Piazza is the place to go if you want to ask questions on homework 0. And chances are someone else already had the same question, and it's already been answered. So
I'm not sure if I'm on the right Piazza because I don't see a homework 0 folder, or is that just going to be homework 1 on Piazza?
Oh, no. Oh, okay. Yeah. There's not going to be a homework 0 folder. You're right. But you don't have to, you can pick like other when you're posting. It doesn't really matter. These folders are just, yeah, they were auto-generated. I haven't had a chance to mess with them. I'll edit one of these. I'll change homework 10 and homework 0. Yeah, but please, everyone, I think right now I see, how many people did I say? 8 enrolled. And I believe we have, yeah, we have 30 something people enrolled in the class. So, so everyone, if you guys can just join Piazza before you submit homework 0. I might add that as a requirement for homework 0. So I have to check that you've enrolled in Piazza too. Give me 1 second. Selena said, Blackboard is insanely slow. Let me try this actually. Let's see if it's slow. It is slow. Ooh, look at this. 503 server is temporarily unavailable. Okay. Well, you know, this is why we pay tuition, right? To fix Blackboard. Okay, so I'm gonna wait for a little bit, because what we're gonna talk about today is it's pretty important. I'm just gonna wait for 4 more minutes till 2:10, and then we're gonna start, because I do want to get as many people as possible. But you know, they can also watch recordings. Another reason to join Piazza, so I can tell you what the lecture link is if Blackboard doesn't work.
Was Blackboard down for anybody else, or is that just my Wi-Fi?
It's very slow. Yeah,
Okay, got you. Cool.
I think it's slow for. Oh, I think it just started working for me. I think it's recovered, so that's good. So today we'll talk about what exactly is Ethereum. Should be an inch. Yeah, it's very slow. I take that back. It's still very slow. Got 2 more minutes. Markets recovered today, so that's pretty nice. It's always good to see some greens after 2 weeks of red. Okay, we've got more people coming in. That's good. Yeah, Blackboard's been down. Just started working. We're gonna get started regardless, though, in 1 minute. Okay, let's get started. Today we'll talk about Ethereum. What is Ethereum? So does anyone? I'm thinking you all have like some sort of some kind of idea about what Ethereum really is. Anyone want to tell me what your interpretation or understanding of Ethereum is? And how it's different compared to Bitcoin, more or less. There's no like right or wrong answer. I guess there is, but it doesn't really matter. It's just your opinion.
Yeah, I'll take a crack at it. Yeah, Ethereum was founded in 2015 by Vitalik. And Vitalik was like big on Bitcoin forums, and he was posting articles and stuff, but he noticed some things about the network that he wanted to improve on. And he basically like suggested that, they add features like smart contracts, but they didn't want to change the protocol. So he went ahead and founded it himself. But Ethereum's main thing is that it has smart contract capabilities and that you can program decentralized applications on the Ethereum network. So it's a step up from Bitcoin because Bitcoin is just peer-to-peer transactions, and you can have like contracts, you can have all kinds of like stipulations baked into Ethereum. But as we know, the gas fees are pretty bad. So yeah, there's a lot with Ethereum, but that's mainly it.
Yeah. So Vitalik, he was I think he was the editor, one of the editors of Bitcoin magazine, I think back then. Today he's 27 years old. And so when he created Ethereum, or I guess co-founded Ethereum, I think Ethereum came up in what, 2014? Something around 2014. So when he was he's probably younger than half of the people in this class when he created Ethereum. Pretty smart guy with questionable fashion choices, of course. Yeah, basically, so Ethereum, it's kind of like Bitcoin, right? So everything Bitcoin does, Ethereum can do. Because Bitcoin's really basic, it's just a digital peer-to-peer cash, electronic cash, and Ethereum can do that too. You can transfer value on Ethereum, but as Cameron said, the highlight of Ethereum is the ability to program the blockchain for it to perform complicated tasks or run programs in a decentralized manner. And Bitcoin, of course, there's also a programming aspect to Bitcoin. If you guys remember, it's called the Bitcoin script. Anyone remember? So it's a stack-based language from Bitcoin. It's a stack-based language from Bitcoin that can only perform really a limited number of things. So today we're just going to talk about what Ethereum is and how it compares to Bitcoin, right? Yes, Colin. I've heard that story. So Colin is typing in the chat. Yes. So apparently he was playing World of Warcraft, and I think he lost some pretty legendary gear, and then he said he cried himself to sleep or something. And then the next day he said and then that's when he saw the evilness of centralized services. I don't know. I'm pretty sure that's like a half joke. I have no idea how real that is.
Still, like, it's still in his Wikipedia or like wiki page, like the second
It is.
one.
I mean, knowing this guy, like, I can't tell if it's a joke or if it's real. But it's an interesting story, regardless, right? Okay, so we're going to talk about what is Ethereum, and then we're going to compare it against Bitcoin. Talk about some of the key differences, and so basically how Bitcoin has an UTXO but Ethereum doesn't, and how they manage state differently, how the block structure is different, how the transaction is different, and the various applications, right? So first, what is Ethereum anyways, right? So the definition is a decentralized open source blockchain with smart contract functionality. Now, Cameron already said before, so smart contracts are basically decentralized programs that live on the blockchain, right? So they're not hosted or controlled in a traditional sense by anyone, because it lives on the decentralized system, and anyone is able to invoke it and interact with it, more or less. And some people call it the world computer, right? Because it's decentralized, so it's worldwide. And then whenever you run the smart contract, it's executed by more or less by every single node. So it's like a world computer, right? And it's also the programmable blockchain, right? And Ethereum is actually, so the language that we use to code in Ethereum, there are multiple ones, but the main one we use is Solidity. And it's known as Turing complete. So the term Turing complete in computer science means that, so if a language is Turing complete, then it means it's able to perform any generalized computational task, although with no regard to the amount of time or resources used. So Bitcoin couldn't do that. So there was Bitcoin script, right? And Bitcoin script, it was very limited because it was a stack-based language and it doesn't have any jumps or loops. So you can only execute it one way, and there's no way to go back or jump logic or anything. And it's intentionally done that way because Bitcoin wasn't designed as a program platform, more or less. It's just designed to be cash. And the script is just a bit of auxiliary utility that's sometimes it's convenient to have it. It's not meant to, the network is not meant to accommodate computation, right? Whereas Ethereum is designed from the ground up as a decentralized distributed computational platform, right? So Bitcoin's lack of Turing completeness, its lack of programmability, it's intentional. And Ethereum has it because it allows a more complex language to be executed, right? So that's more or less Ethereum definition, but we're going to dive deep into it. Let's see. Did Vitalik invent Solidity? I'm not sure. Okay, so the Solidity language is invented specifically for Ethereum. I'm not sure if Vitalik invented the language by himself. but the language is specifically created for Ethereum. Yeah, that's so so this is also why Solidity, it's not very easy to pick up because it's unlike any other language out there, more or less. Because in the traditional programming sense, when you go work for a software company or something, you just say, oh, like, oh, okay, they're using Java, okay, they're using C++. It's a universal language, whereas Solidity is made specifically for Ethereum, and it didn't even exist before. So it's a completely new thing. Although it's inspired heavily by C and JavaScript, I would say. Okay, so let's talk about UTXO versus the account system. All right. Now we talked last time about what UTXOs are. So UTXOs, it's basically it's kind of like a token for you to be able to, that basically says that you really have access to this amount of Bitcoin, right? And in the Bitcoin system, in the Bitcoin network, there is no concept of a balance. So whenever you open up your Bitcoin wallet and you see a balance, it's actually the wallet going back in time and looking at all the UTXOs that you have, and they do that calculation on the fly to determine what your balance is, right? So how can you know your balance? You just go all the way back and start tracing, any UTXO, yes. Oh yes, remind me to turn on live transcription in the future. I forget about this every time. Yeah, so balance is not kept, right? And the way that you calculate it is just go back and then, if it looks for all the UTXOs with your name on it, the input outputs, and then basically input is what's given to you, and then the output is the output is usually two parts, right? One's to the recipient, the other's like your change address, if you guys remember, right? Do you guys remember this? So whenever you're sending someone else Bitcoin, you're consuming your available UTXOs and you're destroying them, and then you're creating new UTXOs, and then usually there's a so one UTXO is locked to the recipient's address, and then the other one is the change address, which is sometimes yourself, but sometimes another address controlled by your wallet, right? Does that ring a bell, more or less, to you guys? How UTXOs work? If it doesn't, it's fine. It's not too important because Ethereum ditches this model. All right, so Ethereum does not use the UTXO model. What Ethereum does is it uses an account system, which is more or less what everyone's familiar with, right? So an account system explicitly notes how much money you have. So instead of like Bitcoin, where the balance is always calculated, in Ethereum the balance is kept. It's kept in a unit called Wei, and 1 Ether is 10 to the 18th Wei. But I usually just use Ether as the unit. Right, Kevin, hang on. All right. Yeah, and you can see here in the screenshot. So this is actually a screenshot from, this is actually how Ethereum keeps its state, and we'll talk about what state is in the future. So in this case, it's basically the balances for different accounts, right? For different addresses. This is how they keep the balance in Ethereum. They keep it explicitly. Now, why do you think that is, right? Why do they keep it? Why can't they use the UTXO systems? So let's talk about the takeaways first. So in the UTXO system, the current state, it is not stored, but it is calculated. It is calculated by going back in time, not going back in time, but looking at the history and then kind of going through all the UTXOs and coming up, and then they have to do a bunch of additions and subtractions, and then they can then determine what your current balance is, right? Whereas in an account system, they just have to read from the database what your current balance is, right? So the current state is actively and explicitly stored, but also all the previous states are stored, right? So the changes, like the history of your balance is also stored, and we're going to talk about how that works in a bit. So any questions so far regarding how balance is stored so far in Ethereum, Bitcoin? It's okay, because we have 2 hours today, and then I don't think we're going to make use of all of it. So we have a lot of time for questions. And if you want to go back, we can talk about some things again. That's totally fine.
Yeah, I have a question really quick. So it is the account, you're saying like an account is stored. Is it stored on like the same concept of a public address built by a public or a private key?
Yes.
Okay.
Yeah.
So all the
Yes.
back end is the same.
What's the same? Sorry.
The back end, like the account system built by public address and private key and all that.
Yes. So the private key and public key stuff, they're all the same. Right?
Okay.
They're not exactly the same, but the concepts are the same. Right.
Cool.
And the only real difference is that Bitcoin doesn't explicitly keep track. You have to do a calculation every time, whereas Ethereum explicitly keeps track of it, your current balance.
Cool. Thank you.
But it also keeps track of all your previous ones, and we're going to see how it does that. Right. Any other questions regarding the account system so far? So you can think of it in terms of like a ledger book. Bitcoin is like a traditional ledger book, but with no like subtotals or totals ever calculated. So every time you want to calculate how much money you have left, you have to go through all the pages and then, come up with the current balance. Whereas Ethereum, in real time, it always updates your most recent balance. If that makes sense. Right. So let's dive deeper into the account system. Right. So in Bitcoin, there's no concept of an account. So the way that and UTXO is yours is because someone else. So again, there are only two ways to get Bitcoin, right? You either mine it or other people send it to you. And basically when that happens and UTXO is generated, that's locked to your public address. Right. And then we use the digital signature thing because again, there is a mathematical relationship between the private key and the public key and public address. So you're actually able to unlock a UTXO with your private key if that UTXO is indeed locked to your public address. Does anyone have any questions on this part? You guys remember? So it's like a public-private key thing from 256. Yes, any questions? Please don't hesitate to ask. We can go over this again. I will assume there are no questions. All right, so, and then when you're sending money to someone on Bitcoin, what you're doing is that you are basically, because you only have their public address, so you're creating a UTXO, locking it to their public address. And what you're really doing is you're saying that only the person who holds the private key to this public address is able to unlock and spend this UTXO. Right? Does that make sense? That's okay. I know it does. It's fine. So again, feel free to stop me anytime. All right. So that's how Bitcoin worked. So there's no accounts. It's all UTXOs. So whereas in Ethereum, there's an account. And so let's talk about really what is an account besides the balance. So because in this screenshot, all you see is a balance, but there are a few more things in an account. Right. So there's something called a nonce that you're all familiar with. Now a nonce in Bitcoin, it's something we use to kind of try to come up with the right hash, right? We're basically manipulating this number so that the block gets slightly different so that you can get a different hash when you're trying to mine stuff, right? You're trying to get below the difficulty thing. You're trying to get enough zeros in front of it. You're basically trying to guess the number. So that's what a nonce is used for in Bitcoin. But in Ethereum, it's used to prevent double spending. And we're going to talk about how that works in a bit. And there's also balance, as we saw earlier. There's also something called a contract code storage. So, because in Ethereum, there are two types of accounts, and we're going to talk about it real quick. And an account can either be owned by a human with a private key, which is what happens when you create a new Ethereum wallet on MetaMask or whatever. And there's another type of account, which is basically a smart contract account, right? And that account does not have a human operator. That account is just a smart contracts program, right? So when an account is a program, then we need somewhere to store the runtime code, right? Otherwise, when you're executing, how do you know how the program executes, right? So we have a contract code storage slot, and then we also have a storage slot. So this is where the smart contract data is stored, right? So there's a difference between the smart contract code and the smart contract data. So let's say I have a piece of logic saying that I have a block of code that says I'm going to take in two numbers and I'm going to return their sum, and I'm going to store their sum in my program state, in my program, right? So the part where it says I'm going to take two numbers and add them and store them, that is the contract code. And then the actual stored number is the contract data. Does that make sense? So the data is actually able to change, but the code isn't. So the logic cannot change, but what's stored could be changed by the logic. It's kind of like when you're playing video games. We all play video games, right? Let's say you play Resident Evil or something. You're playing a single player game, and then there are checkpoints in the game, right? There are save files because that's how they track your progress. Now you can think of the game itself as the code, because whenever you're saving a game, you're playing a game, you're not changing the game itself. You're just saving your progress to a save file, right? So the game itself will be the contract code, and then the save file will be the contract data. Does that make sense? It's also like let's say you're using whatever app you're using. Let's say Blackboard, right? When I enter your grade, I'm not altering the Blackboard software, but I'm writing to its storage, setting a new number for your grade. So that's like the difference. I don't ever change the Blackboard software, but I do change the data that it reads from. All right, so that's the difference between the contract code and the contract data. All right, so that's four things that make up an Ethereum account, just four, nothing too complicated. All right, yeah, so the code is the execution logic and it's immutable, whereas the data, it's whatever that you store inside of it, and that's mutable, right? So as I said before, there are two types of accounts, right? So there are externally owned accounts, which is an address derived from a private key. And now, so an externally owned account is basically, as we said before, whatever. So the account that MetaMask creates for you when you try to use it, or it's something that's owned by a human operator, right? So because it's owned by a human operator, it means that it's not a smart contract, because you can't control a smart contract, because again, a smart contract is a program that lives on the blockchain. It's not something that you directly control. So the contract code and the storage fields for an externally owned account is empty, because again, it's a human being, right? But there's also another type of account called a contract account, which is what happens when you deploy your smart contract onto the network. You want to say something? Okay. So a contract account is what happens when you deploy a contract onto a network, and the address is generated from the I have no idea how to pronounce this, frankly. I'm just gonna say it's the hash of the address of the address and the nonce of its deployer, and it does not have a private key. All right. So a contract account is whenever you're interacting with a smart contract, you have to interact with a certain address, and that would be its contract account, and it would have the contract code and storage fields. Now, smart contracts are also able to hold a balance, right? Because some contracts you're able to pay money to it, and then they'll maybe give you something or whatever. So two types of accounts, right? EOA, I'm just going to start calling this EOA, right? It has a nonce, has a balance, no contract code, no storage. Contract account, there is contract code and storage, and there's also nonce and what is it? A balance. Yes, Jacob.
Whenever someone deploys a smart contract onto Ethereum, and let's say there's a bug in it, and they need to fix that, do they have to deploy an entirely new smart contract? And does that old one still exist somewhere then on chain, sorry?
You see, this is what's so difficult about programming in Ethereum, because once a contract is deployed onto the chain, and as we said before, the contract code, the logic is immutable. It can't be changed. It basically means if there's a bug in your program, and if you didn't build in a way to pause the program or anything, then you're screwed. Because there's no way to erase it. There's no way, you can only deploy a new one at a new address. There's nothing you can do about the old one. It's going to be there. It's going to still be usable if you don't have like a built-in kill switch or like a pause button. So this is what's so different about programming in Ethereum and in other languages, or rather our traditional programming paradigm. Because because even for Windows, you receive Windows updates all the time. There are ways to hotfix the code, right? When you're playing games, there are patches that come out all the time. But for Ethereum programs, at least so for Ethereum programs, there's no simple way to just patch an existing smart contract. You always have to deploy a new one. Now, later on in this semester, we're going to talk about something called an upgradable contract. So an upgradable contract basically uses a proxy to kind of manage which version of the logic are we running on. And then the proxy itself never changes. So the storage is stored in the proxy. But then whenever you try to execute things, it looks for whatever is the most recent version of the contract, and it does the execution logic over there. So that's like the gist of upgradable contract. It's upgradable, but then the old code still exists, right? But because the proxy holds the storage, so it doesn't matter if the old code is broken. You just have to deploy a new one before anyone really messes with it. And then now you're using the logic of the new one. So it's a little bit complicated. We're going to get to it later on in the semester. But yes, so when we're starting off, and before that pattern existed, there was no way to fix any bugs in a contract that's already deployed. The best you can do is pause it. But like if let's say you're building some kind of some game, or you're collecting money for servers or something, and if let's say you forgot to build in a way for yourself to withdraw money, then you're screwed. The money will be stuck in there forever because you never programmed a way to withdraw that money. And there's no way to, sure, you can deploy a new contract, but the money is still stuck in the old contract. And there's nothing you can do there's nothing you can do to get the money out. So this is why programming in Solidity is so hard, because nowadays it's much better, but before, earlier on, you could not afford to make any mistakes, and it was even more difficult because the language first came out and nobody knew what they were doing. Yes.
So I'm trying to understand. A contract account does not have a private key because it's basically in the code how to access.
Yeah. So a private key, having a private key implies someone owns it, right? But the smart contract doesn't. So a smart contract is not owned by anyone, so it doesn't have a private key, more or less. And you see that the address. So the address of a normal human operated account is derived from the private key. Same process as the Bitcoin thing. A little bit different. Like Bitcoin is base 56. I think this is just hex. But the process the process of turning a private key into a public key is more or less similar. right? In Ethereum, Bitcoin. So that's for a human operated account. But for a contract account, the address is just the hash of the deployer's public address and the deployer's nonce. That counts, we're going to talk about how nonce prevents double spending. But yes, Ben. But yes, the contract accounts do not have private keys. And this has implications because that also means contracts cannot digitally sign things in the conventional sense. Because remember, digital signature is generated by the private key, and then you use the public key to verify it, right? But then how can you sign something if you don't have a private key? So this is something interesting that we're going to talk about. And yes, Ben.
Yeah. So quick question. So when I'm like looking through like a block explorer, and then I could see like maybe I made a swap or I did a bridge, and like there's like transactions to like these random addresses, like those are the contract accounts, right? They're like facilitating these trades.
Yeah, like if you see like a Uniswap router or something, these are contract accounts. Yes.
All right, thank you.
Yes. So whenever you see someone calling some functions on an account, then that account's got to be a contract account, because again, an EOA does not have any contract code, and a function is a part of code. So for EOAs are in smart contracts, so an EOA and a contract account, they cannot be the same account. They must be different accounts. Now there are now Ethereum, they're working on a new proposal that kind of combines the two into one, that allows the combination like that. They're trying to work something out where they're trying to allow an EOA to also carry some logic, but that's been stuck in the proposal stage for like 2 years, I think. But that is something that they're looking into. But right now, an account's either human operated with no logic, or it has logic and it's not run by anyone. Right? Any other questions? These are great questions. I love questions. Okay, that's it. So that's all about accounts, right? And yeah, you know what? Actually, before we move on, let's briefly talk about how a nonce prevents double spending, right? Now we talked about it last time, but I just want to ask: does anyone tell me what a double spend is? Don't be shy.
When a single token is like being spent once, being spent twice.
Yes. So a single piece of digital asset is being spent multiple times, right? Now, how does Bitcoin prevent that from happening? How does Bitcoin prevent me from taking a UTXO and then, consuming it multiple times?
Doesn't it destroy it? Like if I send you a UTXO, it'll destroy mine and then it'll create a new one for you.
Yes. So the way Bitcoin does that is it literally destroys the input UTXOs. So you can't double spend it, right? But for Ethereum, it doesn't use an UTXO, right? Then what's stopping me? So let's say I have a transaction. Let's say I create a transaction that basically says I'm gonna do something, send some amount of money to someone, and then what's stopping me from just duplicating that? Or reverting back or doing whatever. If there's no UTXO, then there's nothing destroyed. What's stopping me from copying and pasting my tokens? Right. So there's something called a nonce. So a nonce in Ethereum. So whenever you make a transaction with your account, your nonce is always bumped up by 1. It increments by 1. So that basically means that any transaction, if the nonce is lower than the current account nonce, then for a certain transaction, if the nonce of that transaction is lower than the nonce of the account, then that transaction will simply be invalid. It'll be dropped. So it's a way that prevents people from basically from spending some money and then spending some other money and then going back and doing that, because then the old one will be invalid because the number keeps going up. Right, so it's basically a way, so it basically announced in Ethereum is a way to invalidate stale transactions. Yes.
Just to repeat what you said, so you said when a transaction is made, and the nonce will be increased by 1, and if the nonce is higher than the account, then the transaction will just be canceled.
Yes. Yes.
Okay, thank you.
Yeah. So double spending. So basically, if a nonce is set to the same nonce, if there are if you submit 2 transactions at the same time, only so when the first transaction gets mined, the nonce will increase, and then the second one will basically be dropped because then it will have the same nonce. So this is a way to basically stop people from, let's say, in the same block, right? In the same block, I'm gonna have two transactions because I'm trying to spend the same amount of money twice. I'm gonna have 2 transactions in the same block that sends the same amount of ether to different people. Right now, if they both go through, because the starting, so when I first start my, when I'm starting the transaction, starting the block, my balance, let's say, is 10, right? So what I'm trying to do is I'm trying to make my balance go down by only 1, but I'm submitting 2 transactions and basically trying to spend the same ether twice. But then what's going to happen with the nonce system is that when the first transaction gets mined, my nonce will be bumped up by 1. And then, when I would get to the second transaction, the nonce would be because when I created the transactions, my balance was 10. And then my account was at the state when my balance was 10. So the nonce would be, let's say, 2, right? So that both transactions would have a nonce of 2. And when the first transaction gets mined, the nonce will be bumped up to 3. And when I try to process the second double spend transaction, the nonce of that transaction will still be 2. But then now my account nonce is already 3, so it doesn't go through. Yes.
So is the nonce basically like a transaction ID for like being on chain, or am I thinking about that wrong?
It's a transaction counter.
Okay.
It's not a transaction ID. So it's a transaction counter.
It's a transaction counter, but can that counter be used to identify like individually like things that don't overlap? So it's like almost like sort of an ID, or is that not a use case of it at all? So
it's not an ID. It's an ID for your account. It's an ID for the transactions in your account, but it's not a general ID.
Okay.
Because if we're both starting off the new account, then our nonces would both start from 0. So that doesn't work. Right. But within the same account, it's basically preventing people from sending out 2 transactions that try to spend the same amount of money to different people. Because let's say I have 10 ETH right now, right? I'm trying to send someone 1 ETH. I'm trying to send 2 people 1 ETH simultaneously. I am creating 2 transactions at the same time, right? And then because I'm creating them at the same time, my starting balance is the same. It's both like 10, right? 10 ETH. Then if both go through, because both of the starting balance is 10. So after they get mined, I would be left with 9 ETH, but then I would have successfully double spent my 1 ETH. But then with the nonce system, because with every transaction mined that's specific to your account, the number gets bumped up by 1. So that when the second double spend, you're trying to do that, you're trying to mine the second double spend transaction, the nonce would still be the old nonce and it wouldn't be the new nonce. And then the system can tell that you're trying to push a stale transaction, it would just cancel it.
Got it. Yep.
This part is a little bit confusing. Yes, Chase.
Is there still a public ledger where all of this is tracked? Or like how would the auditing work for this?
For what exactly?
for like tracking whether like double spending or if a transaction has been, yeah, I guess spent twice? Like how would you audit this in practice?
Yeah, so so this system prevents double spending. So there won't be any double spending, right? And the non-balanced contract code and storage, they're all transparent on the blockchain. Like you're able to see them for each account, right? So they're stored in a structure like this. It's called a JSON structure. It's so basically it's like a key value map, right? So given and then given a public address, you're actually able to see their nonce, their balance, their contract code, and their storage.
What if the user is actually trying to send two like valid simultaneous transactions, or is that just like not possible? Like how would
That is possible, but then this is why so in order to send two transactions at the same time, what you do is you have to send them in order, right? So you first create the first transaction, and then locally you update the state of your account. And when you update the state of your account, let's say, let's use the same example, right? Let's just say I have 10 ETH to begin with, and my nonce is 0. All right. I'm trying to send Chase 1 ETH, and I'm trying to send you Roman 1 ETH, right? If I want to double spend it, what I do is I start off with the state of my account at 10 ETH with 0 nonce. I'm going to create a transaction that sends money to Chase, 1 ETH to Chase, and then my new state is 9 ETH with the nonce being 1. Do you agree? But then because I'm a scammer, I disregard the new state. I go back to the old state again. And then I try to create a second transaction that's not based on the new state, but based on the old state. And then still, because it's based on the old state, I magically have 10 ETH again, with the nonce being 0. So now I try to send you, Roman, 1 ETH. So the transaction that sends 1 ETH from that I send 1 ETH to you again, it's gonna contain 1 ETH, and then the nonce will be 1. And then at the end of both transactions, my new state would both be my balance being 9 ETH and the nonce being 1, right? But what's going to happen in practice is that if I process, if the other miners mine the transaction where I send Chase 1 ETH first, the new state will be 9 ETH and 1 nonce. But then when I get to your transaction, Roman, your transaction nonce will still be 0 because the state was 0 when I created your account, because I reverted back. I'm trying to double spend. But then the other miners see, oh, the nonce of this is lower than the account's current nonce, so it must mean it's outdated. It doesn't even assume you're trying to double spend. It just means it's outdated. So that's like, and then it just gets discarded.
Okay, so when you say like you update it the balance locally, does that mean like the user has to manually, like, say they go from 10 to 9 to 8 for it to be
that's
validated?
managed by the wallet, and usually the wallet connects to, so a wallet doesn't hold the blockchain, it connects to a different node that holds the entire blockchain, and they do a bunch of stuff there. So the right way to send two people money in the same block is I send Chase 1 ETH first, my nonce goes to 1, and then I send you 1 ETH based on the new state, not the old state. So now the new state is my balance is 9, my nonce is 1, and then I send one more transaction to you, and then my balance becomes 8, my nonce becomes 2, and then that's how we're able to do things.
Okay, got
So
it.
we have to do it sequentially. Yeah. Yes.
So are nonces typically very high for people that make a lot of transactions, or are they reset after a certain time?
They're not reset. Yes, it just keeps going up.
Okay, cool.
Yes, but internally, it's I don't think you can ever hit the limit, to be frank. Yeah, it's
so there's no limit. There's no limit.
I mean, there is a limit. I think it's 256 or something like that, of that magnitude. So you won't ever be rich enough to pay all the gas fees.
Okay.
But Roman, that was so remember how I said when other miners see that a transaction has a lower nonce than the account's current nonce, it just discards it, right? So this is also a way for people to push through transactions if they get stuck due to the gas fee being too low. So let's say I'm trying to send you some money, 1 ETH again, and then I was too cheap. I didn't want to spend any more money on gas fees, right? And what's going to happen? The miners will deprioritize my transaction because they don't get money out of it, right? And then when they deprioritize it, sometimes, like, depending on how little gas fees I send, sometimes it would mean that my transaction, like, some people have had their transaction stuck for a month. And let's say I want you to get the money like immediately, but then, what am I going to do? Like, I already submitted this transaction that, that I'm sending you 1 ETH. So my balance has already like gone down, but like it's already been sent, and I don't want to, like, how can I cancel that transaction, right? So the way to do that is basically immediately send a new transaction with the same transaction with a higher nonce, and that would just automatically discard the old one.
So you can like kind of force like a double spend for the one that you actually want to go through.
But it's a single spend because the old one gets discarded, so the old one doesn't count.
Yeah. Okay. Got
The
it.
new one has a higher nonce.
Mhm.
Yeah. So that's usually how people push through. And then, I do this too. Like, sometimes I sometimes when I try to do like a swap or interact with a smart contract, when the gas I send over is too low, it gets stuck. I just try to push it through with higher gas, with a higher nonce, and that's just going to discard the previous ones. Yeah. All right, so that was enough about UTXOs and accounts. Any more questions, by the way?
Yeah, just to clarify, can you hear me?
Yes.
Okay. So if the nonce of a transaction is lower than the account's nonce, then that transaction becomes discarded. Is that correct?
Yeah.
Okay. Thank you.
But in reality, honestly, this is just for your knowledge. Like, when it comes to programming Solidity, you don't ever have to know this kind of stuff. So basically, I'm just trying to give you some context as to how Ethereum works. Probably, honestly, the only time you have to worry about nonce is when you're trying to interact with the contract and you get stuck because you cheaped out on gas fees and you're wondering, how can I push it through? And then what people online will tell you to do is, go to MetaMask and then submit the same transaction, but force enter a higher nonce, to force the chain to abandon, to discard your old transaction. That is literally the only time that you're gonna run into the word nonce on Ethereum. Yes, Sean.
So if you do like put in a higher nonce and it pushes the transaction through, do you get the money back from the old transaction?
It will be as if the old transaction never happened.
Okay, so
because when a transaction is
get
stuck, it's going to be in the pending state.
Yeah.
It hasn't been applied yet.
Yeah. Okay, got you.
Yeah. So what you're doing is you're submitting a new transaction and then also kicking the old one out of the pool. So it doesn't. So I'll never count. It will just disappear. Yes, Jared.
Wait, it just slipped my mind. But does that mean that you have to pay gas fees both times? So when you want to cancel the transaction, you also have to pay the gas fee?
So you cannot cancel a transaction. You can only replace it with another one.
Yeah, so that means when you replace.
But the transaction fees for the old one will also be refunded to you because it never happened.
Got it.
Yeah.
Thank you.
So the gas fees and everything, they don't get deducted until the transaction goes through. So because the old one has never gone through, so it just never counts. Sean?
So what would happen if you didn't end up replacing that transaction? You just leave it for like an extended period of time?
Yeah, it would just stay there forever.
It just stay there.
Whenever if some miner decides to pick it up, then it will get picked up.
Yeah, because I'm in that position now. That's what I'm asking.
Yeah. If not, then you'll just be there forever.
Sounds good.
Especially now, like it's not like, you know, the network is free at times. It's always under load, right? So there's always people that's paying a higher gas fee that are trying to get their stuff through. So they might just never get to you.
Gotcha. Thank you.
Yeah, yeah. Any other questions? These are all very good questions. All right, no more questions. And this is really mostly just for your information, so you have an idea of how things work. But in terms of coding, you're never going to touch these. Not these, but the nonce stuff, right? So you're never gonna, so in Solidity, you're never gonna say, I'm gonna read the nonce of this account. You're not gonna do that. You're never gonna say, well, these, you're gonna get involved a little bit, but the nonce, you'll never touch it. The only times you'll ever have to touch it is when you're trying to push through a transaction. It's just like how in Bitcoin, you never explicitly create your own UTXO. It's all handled by the software. All right. So that's UTXO versus the account system. So you can see that with the account system, we're able to store a lot more attributes, right, for a certain account. And this makes it a lot more flexible and a lot more powerful than a UTXO system where the only thing that gets pushed through is, you know, the amount of money that's locked to someone, right? But, you know, but also Cardano or Cardano, however you pronounce it, Cardano, they're using a UTXO system to do smart contracts, and I'm not too sure how they're doing that. But as you might have observed before, because you don't remember how I said, Roman, when I did the analogy about sending Chase and you money that we have to do in order. This also presents a bottleneck for this system where you cannot do things in parallel. So the state changes have to be sequential. Whereas in a UTXO system, it doesn't matter. It could be, you can do things in parallel because you know, they're just UTXOs. Like one UTXO doesn't depend on another. Whereas my current balance depends on my previous balance, if that makes sense. So UTXO system could be faster in some aspects, but we're not going to get into that. That's just like an offhand comment, right? So the Ethereum state. So I talked about like account states and whatnot, but what are states in Ethereum, right? So in Bitcoin, the balance is again calculated by aggregating UTXOs, right? But in Ethereum, because it's a platform with code in it, with like smart contracts and programs, we have more things to worry about than just transactions, right? So the idea is basically we have too many things going on in Ethereum, right? Because let's say you're interacting with, let's say you're doing DeFi stuff, you're trying to stake your money or something, then you interact with your smart contract, and then you modified your storage, and they basically keep track of who's staking how much, more or less. Although they do it slightly differently, but because they sometimes issue like a receipt token. But let's say they're keeping track of it internally, right? So there are a lot of things to keep track on Ethereum, and it's not practical to calculate the state of thousands of decentralized applications on the fly by going into the past and replaying everything like what Bitcoin is doing. It's not practical. So this is why Ethereum always has to storage the current state, because it's just faster that way, right? So the general idea is that in Ethereum we have to keep track of the state of things, right? So that's where the word state comes from. So calculating state. So again, in Bitcoin, what happens is that the clients, they usually they calculate it on their own, and the chain doesn't keep track of the current balance or the state. Now, most of the time when you're using a wallet, they probably connect to their own server, and their server has like a lot of things cached. So that's why you can see your balance pretty much instantly. But really, you have to redo the calculations. You can't just read a number off of some data on the chain. There's no such data. You have to calculate it yourself. Whereas in Ethereum, everything is explicitly stored, right? And that includes the most up-to-date and recent state. It's also explicitly stored You just have to read the single attribute and you know how much your balance is, right?
So is that why the block time is so much shorter for Ethereum? Because they're just reading from the latest state, whereas
not necessarily. The block time doesn't have too much to do with that. The block time is more about how usable the chain is, right? Like imagine, because they envision smart contracts, they envision Ethereum to be used in everyday interactions, although it's pretty unrealistic given the gas fees right now, right? But just imagine, let's say you're trying to interact with some program in real life. And if Ethereum had the block time of Bitcoin, you have to wait 10 minutes for every action, which is not very good, right? Whereas Ethereum is 10 seconds. So that's a lot more usable, right? And there are other chains that go much faster. Phantom Avalanche, I think they have like 1 to 2 second block times. Solana is measured in the milliseconds. Although, you know, how decentralized it is debatable. I'm not saying if it is or it isn't, but it's debatable. But Ethereum is 10 seconds. And it doesn't have too much to do about the state. It more has something to do with how useful it is. And, you know, and you have to think about when Ethereum was created, was conceived in 2013, 14. Back then, the only other blockchain was Bitcoin, more or less, right? And they had a 10-minute block time. So 10 seconds was already a pretty big jump, right? And especially back then, you know, they have to consider, because, you know, the faster your block time is, what do you think some of the challenges would be?
What are some of the challenges?
Yeah. So think of block time as, so imagine you have your friends sitting in a circle, and let's say you're like, let's play a game. Let's still play that game of, you know, you say something to the next person, and then the next person says something to the next person, and then it goes all the way around, right? But in this game, let's not consider the correctness of the final statement. Let's just consider how much time it takes to go around. So how much time it takes for everyone to get onto the same page. And it doesn't even have to be sequential, right? But then the faster you go, the harder it is to keep everyone on the same page. So that presents a networking and synchronization challenge, right? Let's see what's in the chat. Consensus, yes. So it's harder that way. And this is also why some of the more, like Solana, it's I would argue it's pretty centralized right now. Just because like the block time is just insane on Solana, and it's fast, it's very fast, but like there's no way a network, like a global network can keep up with that. Like if you've ever played games with your friends from Europe or Asia, you know, like it's like you play some online games and you see your ping is like 200 milliseconds or something. You know, there's a very, very, very real and physical network delay that's very hard to overcome, right? And then when you have a block time that's too fast, it's like half of it's going to get lost in just trying to reach the other person, and, you know, not even trying to form a consensus, you're just trying to reach them. And then what if there are, you know, what if there are arguments or whatever, you know, what if there are, you know, disagreements? Then, you know, and then everyone's constantly playing a game of catch up, where, you know, it becomes very chaotic very quickly. So so we're going a little bit off topic again, but that's basically that's kind of the challenges of a blockchain with super low block times, right? So coming back to the state thing, right? So let's take a look at the Bitcoin state transition. This is just a fancy word of how a transaction or a block changes your account balance, right? So let's say this is the previous. So let's say this state on the left is the previous block, and this state apostrophe, whatever, the state prime is the next block, right? And in between, there's a bunch of transactions. This is just saying that what Bitcoin does is that you see how, so these are basically the addresses and their balances, all right? So you can see that we start off with these balances, and this guy 7B whatever, he had 1 Bitcoin, and then they're spending 1 Bitcoin, and then they're creating new like UTXOs and whatnot. Okay, so these are actually UTXOs, my bad. So basically in Bitcoin, you're destroying, you're spending UTXOs and you're creating new UTXOs, and that's how the state's managed. It's very simple because there's nothing else to worry about, right? All you have to worry about are UTXOs, right? There's nothing else. You create them, you destroy them, and then you create new ones. It's just a game of adding and subtracting UTXOs. There's nothing else, right? Does everyone understand how this kind of thing works? So you're spending a UTXO with 1 Bitcoin. You're basically combining these 2 UTXOs, and you're spending 3 Bitcoin. See, you're spending 1 and 2, and then you're creating some new ones. So you're just kind of sending it to someone, but you're destroying the old ones and creating new ones, right? So this is how it works. Yes.
How come there are 3 new UTXOs being created when there's 2 being spent or destroyed, I guess?
Yeah, so you can create any number of UTXOs as long as the values add up. As long as your output is not more than the input, you can create however many ones you want. But it's probably not efficient. It's most efficient to create the minimum amount of number of UTXOs, but technically you can create like a bunch of them. Yes. Does that make sense?
Yeah, that makes sense.
Yeah, so you can break the same. So let's say this UTXO that holds 1 Bitcoin. This is meant for Roman. Let's say I can easily split it into 2 UTXOs of 0.5, or can do 0.4, 0.6, whatever, and it can be both locked to Roman's account, and that would be the same as having a single UTXO locked to Roman's account or address. Right, so you can create however many UTXOs you want with any amount of Bitcoin, as long as the sum of your output does not exceed the sum of your input. So you're not trying to spend money that's not there.
Okay, what's the point though of having a UTXO with the balance of 0, like here?
No purpose.
Okay, cool.
Sometimes people do that. So because you can also in the Bitcoin transaction, you're able to attach a short message. Actually, no, that's a transaction. For UTXOs, really, there's no reason. This is just for illustrative purposes. I mean, of course you can, but there's no reason to. And all it does is it just blows up the database, the blockchain database that contains all the UTXOs. It has no real purpose. Like, it's like saying I'm giving you $0. Like I'm gonna, let's say, like I'm gonna write Jared a check for $0. Like sure, I could do that. There's no real reason for me to do it, but there's nothing stopping me from doing it. Right, writing a $0 check, I can do that. Does that make sense?
Yeah, thank you.
So it's a waste of resources for no real reason. And there's nothing stopping you from doing that, but it's not very clever, right? So any questions on this kind of illustration? I will lower your hand. All right. So yeah, so calculating the Bitcoin state, right? So what happens? So first, for each input in a transaction, right, you verify the validity of each UTXO, right? So you check their digital signature and whatnot. Oh, that's what I just said. So you check the digital signature, and then you verify that the the sum of the inputs it's larger than the sum of outputs, right? And then the input ones are deleted and the output ones are created, right? That was how Bitcoin does things. Now you see in Ethereum, it's a lot more complicated. And just by looking at these, you can tell the difference in complexity between the two languages. The two blockchains, right? Bitcoin, it's just UTXO, very simple. Whereas in Ethereum, you have this first guy, 14C. So this is a EOA, an externally owned account, right? Because it doesn't have code. this one, BB7, right? Now, BB7 is a contract because you see it has contract code, it has storage. So you see this is the balance, this is the contract code, and this is the storage. This is like an array or like a collection of things, right? And also you notice we never mentioned nonce ever, because really it's like you don't have to really know how it works too much. And A92, right? This is also a contract, right? Because as code has like a storage. And 409, this is again an EOA because it only has a balance, it doesn't have anything else, right? So this is the old state. And for this transaction, right? So this 14C person, right? It's trying to do something to the BB7 contract, right? And the value is 10, meaning that it's sending over 10 ETH. The data is 2 and Charlie. So let's see what it's saying. It's just saying that it's just basically trying to interact with the smart contract and modify the smart contract, right? And then the signature, you don't have to worry about it, right? And you see that after this transaction, you see, because 14C, so because the value of this transaction is 10, see that the balance of 14C decreased by 10, right? So from 1024 to 1014, right? And then you can see that the balance of BB7 went up by 10, right? 5202 to 5212, right? And then for the data, right, it interacted with this. So you can see that, you can see how the code stays the same. The logic never changes, right? So this if contract storage, whatever, this one never changes, but the underlying storage with the bracket, see how it changed, right? The 0 turned into a Charlie, right? So this is again to illustrate how, the difference between smart contract code and data. But this is also to illustrate, see just how complicated a single Ethereum transaction could be. Like a single transaction can modify a number of things. And if you don't keep track of the current state, like if you're just trying to do things like how Bitcoin does it, if you're just trying to go back and recalculate everything, the amount of calculation it's too much, right? So this is why Ethereum needs to keep track of the current state of things, right? Just because there are too many things to keep track of. Yeah, so calculating the Ethereum state, right? So the first step is to verify if the transaction is valid. Right now, not malformed, meaning that it's in the correct format. The digital signature is valid. And you see the nonce matches the sender's nonce, right? I lied, I said you'll never see the word nonce again, but I promise you this is the last time you're gonna see it, right? And then we execute the transaction, right? So for a fund transfer, we check if the sender has enough ether, right? And for a contract call, we execute the contract code. Now in this case, we have both, right? Because we're sending this transaction with both value and data, right? Now value is how much you're sending over. Data is only used for smart contract interaction. So you're both sending over money and you're also interacting, right? So it first checks the balance. Is 1024 larger than 10? Yes. So, this guy has enough money. And then, the interaction, we can execute the contract code. Now, if the execution is successful, then, the transfer is completed and then the storage is updated. Now, in any, at any step, if let's say the sender does not have enough ether, or the contract call fails, or there's a safety check or some kind of check in a code, and it fails to check, the entire thing rolls back, right? So Ethereum transactions is something we call atomic, meaning that it's all or nothing. Either everything happens or nothing happens, right? So this prevents something going through halfway and corrupting everything, right? So this is true for all blockchain transactions, I would say. So all blockchain transactions are atomic. Either everything goes through or nothing goes through, right? So that's more or less how the Ethereum state is transitioned. Any questions on the Ethereum state? No questions. It's just a lot more to keep track of on Ethereum. That's the general idea of it. right? So now we come to the block structure of Ethereum, right? Now this is an anatomy of an Ethereum block. It looks very complicated, but we do see a few familiar faces here, right? We have the parent hash, which is the hash of the previous block. That's how you go back, right? We have the Almer's hash. Apparently it's a trendy word for uncle. It's the uncle hash. Now, what is an uncle in Ethereum? Does anyone remember what is an orphan block in Bitcoin?
Yeah, isn't it a block that didn't get accepted in consensus, so it just kind of got rejected and never got put into the blockchain?
Yeah, so when two miners come up with a puzzle at the same time, more or less, right? Then who should the network listen to, right? Because they both came up with the puzzle with the solution, and they're both valid blocks. What happens? So what happens is that they're going to then compete for the next block, like who gets there first, and the next one, and then whoever loses this will become the blocks that they mine will become orphan blocks. And in Bitcoin, orphan blocks are not rewarded. So the miners that mine the orphan blocks, they will not receive any mining rewards, which is very unfortunate, because their answer is just as valid. They just couldn't compete, right? But in Ethereum, uncle blocks are still partially rewarded. Like you still get a participation trophy. So that's what Almer's hash is. It points to an uncle block. If any uncle block exists, you don't have to worry about this. I'm just explaining. The beneficiary is the recipient of the address that receives the mining rewards, right? And we have we can ignore the roots for now. We'll explain it a bit. Logs bloom. We don't have to. It has something to do with events. We don't have to worry about this. Difficulty. That's difficulty. The same in Bitcoin. Number, I believe, is the block height. Gas limit and gas used. That's just so each block in Ethereum has a maximum amount of computation allowed, right? So that's what the gas limit is. And the gas used is how much is actually used. And the limit is the upper cap of it. And it adjusts automatically within a range based on network demand. Right? And as said, logs bloom is the bloom filter used to filter event logs. We don't have to worry too much about this, right? And we have timestamp, which is just timestamp. Extra data, mix hash, like we don't have to worry about these. Then we have the block nonce, right? And that's again the same nonce as in a Bitcoin block. It's like it's just used for proof of work stuff, trying to get the right hash, right? Now, if you want to, let's check this out actually. It's open link. I have to do a new share. Yeah, so when you run git block, this is what you get. All right, so this is what you're going to see in code, the stuff in Ethereum block. There's like the difficulty, extra data, I don't have to worry about it, gas limit, gas used, the hash of it, who's the miner, which is like the beneficiary, what's the nonce, number, and then the parent hash, timestamp, and also a list of transactions, right? So it's pretty straightforward. It's nothing too confusing. Let me know, stop me anytime you have any questions, right? But then, and then, yeah, go ahead.
When you said it was a list of the transactions, so is it actually a list or is it like a hash of the list? Like
yes, it's hash, and then you get the individual transactions separately. Okay, cool. Thanks. Yeah. But this is just like how this piece of software works. This is like it's just like a framework that you use to kind of interact with the blockchain. Because if they were to include the details of every single transaction, then it would be too much information, right? So let's see. So get transaction. You see, for get transaction, this is a whole bunch of data again. So if you include all that data in a single call, it's going to be too heavy. That's why they only include the hashes, and depending on what you're looking for, you can go look for the details in more detail. Yeah.
Cool.
So,
Thanks.
yeah. Right. Oh, whoops. But then where's my Merkle tree, right? Remember in Bitcoin, there's like a Merkle root, but then now we have state receipts and transaction roots. Now, what is this, right? So they serve the same purpose as the Merkle tree does in Bitcoin, right? So actually, they are like, we call them state receipt and transaction roots. They themselves are Merkle roots, right? It's just because how complex Ethereum is, they have to split the data into 3 different parts instead of Bitcoin, where they just track everything with a single Merkle tree, right? So the state tree, by the way, this is like pronounced tree, it's really weird. So the state tree, it records the account state, so your balance and all that, right? The transaction tree records your transaction requests. So basically, let's say I'm trying to send Jared 1 ETH. That's what that one records. The request, like the transaction itself, but not the execution, just the transaction. And then the receipts tree is the outcome of the transaction. So what's the outcome of me trying to send Jared 1 ETH? The outcome is that Jared got 1 ETH. So that's actually separate from the transaction tree, and that's in the receipts tree, right? So basically, instead of a single Merkle tree, we now have 3. Does that make sense? All right. So the reason why we have these separately is because they exist to allow us to verify very quickly and easily, right? We can check if a certain transaction is in a particular block. We can do that with the transaction tree, right? Because, right, so that's how so that uses the transaction tree. And we can filter event logs. Now we can skip this one. We're going to talk about event logs in the future. But we can also look at the state tree to easily verify the current balance of an account. And we can also see if an account exists or not. And even in the state tree, remember the state tree, so remember what's stored in an account, right? So a state tree, we said, stores the account state, right? And an account could either be an externally owned account or a contract address, right? Or a contract account. Now, and in the contract account, what do we store? We store the contract code in storage, right? So basically, we can use the state tree to verify the current state of a smart contract, what the logic is, and what information it holds, right? And now that we know what the current state of the contract is, we're able to retrieve that state and then simulate a transaction locally without publishing it. It's called a dry run. Yes, this makes sense. Right? So basically, we're able to download the smart contract at its current state. And then we're able to perform fake actions on it just to see what happens. Right? And then this is actually a trick that we use not anymore, because I think the frameworks do that for you. But what we used to do is that we used to do a dry run for every contract call, just so that within the dry run, we all know that if it's going to fail or not. And if it fails, then we don't have to waste time submitting it, like sending it onto the chain. And when it fails, your gas fees will still be consumed. But then it failed. And you're going to be left, you're going to basically, you're going to be left with no gas, but then it also failed. So you're actually able to see if something's going to go through more or less by running it locally as a simulation. Does that make sense? It's kind of like, I'm not sure if this is a good analogy. It's kind of like calculating your final grade before the exam to see how much effort you have to put into it, instead of just going into the exam and seeing how many points are you really going to get afterwards, right? You always want to try to do a simulation first. So it's like downloading your grade book at its current state and calculating how much you need on the final, that kind of stuff. So you're able to download a contract, and then do things to it to simulate the outcomes, right? Does that make sense? Does that not make sense? Any questions? And you don't have to worry too much about these, right? This is more of a this has less to do. This is very concept heavy, and this has less to do with coding and more to do with just knowing how Ethereum works in general, right? So a test net, not necessarily. So Prithvi asked, is that what a test net does? No. So a test net allows you to play around with things in real time and to submit transactions for real. But then you're using a test currency, so there's actually no real world consequences because it's not real money. But then a dry run never even submits the transaction. It just simulates it locally, if that makes sense. And there are implications, right? So if you simulate a transaction locally, you get the result instantly. But then if you submit it onto your chain, you have to wait for like whatever the block time is, right? Or it depends on how many confirmations you need, that kind of stuff. But if you do it locally, you just get it instantly. So that's the difference. That's a good question, testnet. We're gonna get to it next week or maybe the week after. Right? Any more questions? Again, I am not going to ask detailed questions regarding these on the test. These are more for your information. To be honest, they don't have a ton to do with writing smart contracts, but I think it's good to know how Ethereum works in general, right? But I'm not going to be heavy on these stuff on the tests, all right? How to access the slides. Yes, we have friends from outside of class in our lecture too. I'm going to post these on Google Drive maybe. Yeah. All right, so with that out, with the block structure out of the way, let's look at transaction structures, all right? It's very easy, it's very simple, right? It's just a nonce transaction, so that's the account nonce that we talked about. Gas price, gas limit, to value VRS data init. And init, just don't worry about it. A VRS, we'll explain a bit. And the value is just how much you send over, and you know, so we're gonna kind of dive into it, all right? So the nonce again, we use it to prevent double spend. I lied again. This is actually the last time we're gonna see it. So we don't have to talk about nonce too much because we talked about it. Gas price and gas limit. So this is more interesting. So the gas limit is how much, so the gas limit is the maximum amount of computational power that you're willing to, that the transaction will possibly consume, right? That's the gas limit. So it's like an upper bound for the amount of computation that you require, right? So that helps the network to kind of gauge what's the worst case scenario for your transaction, like how much computational resource does it have to devote to this single transaction, right? And we're going to talk about these in detail in a bit. And two, it's just the address of the receiver, right? So it's either a human-owned account, EOA, or a contract address if you're trying to interact with the contract, right? And the value is strictly like any money transfer, right? And in the VRS, So VRS are three components that make up an ECDSA signature. So an ECDSA signature is actually able to be spliced into three parts, which are VR and S, right? So you don't have to know, you just have to know that VRS are they are mathematically related and they make up an ECDSA signature. All right. And let me actually find an example. Yes, here we go. You know what? I can't find it. That's fine. So I was trying to find an example where you can see what the VRS values are exactly. But you don't have to worry too much about it. Actually, yeah, you're able to see it. So this one. Yes. Okay, are you able to see this one? So you see the V, R, and S, right? There's three values. These three values make up a raw ECDSA signature. That's all you need to know. You don't have to know how they work. I don't even know how they work. I just know that you can combine them and disassemble them. You can combine the three of them into a valid signature, and then you can disassemble a valid signature into three parts, right? And data is any input data that's used to interact with the contracts, right? So if your receiver is an EOA, then the data field is usually left blank. And if it's not, I think it's just ignored because there's no contract code of any kind. It's probably even going to revert because there's no code, right? So the data, see that there's the data field here, right? When we talk about the state transition, it looks more complicated than this. But that's like the gist of it. So that's what we use to interact with the smart contracts, right? It's by using the data field. All right. So here let's talk about gas limit and gas price. All right. So limit is the max amount of transaction fee units you're willing to spend on a transaction, right? So and transaction fee units. Sorry, the transaction fee represents on Ethereum a computational cost, right? I mean, it's the same on Bitcoin. It's just how, well, it's actually a little different than Bitcoin because on Bitcoin, there's little to no computation at all. It's just processing UTXOs, right? But on Ethereum, because we actually have code that's being executed sometimes, so the amount of, so depending on how complex a smart contract is, the more complex the contract that you're interacting with is, the higher the transaction fee will be. Just because the contract is very complicated, so it requires more steps to be executed, which translates into more computational cost and then translates into a higher transaction fee. Right? Does that make sense? Does that not make sense? Any questions? Okay, so yeah. Any questions? I saw Jared turn on his webcam. Okay, no questions. All right. So the gas limit is then the max amount of transaction fee units we're willing to spend. Why do I call it transaction fee units, not just transaction fees? Because for each unit, there is a price that you're willing to spend, right? So usually you cannot modify the gas limit, right? You cannot modify the gas limit, but what you can modify is the gas price. So the gas limit is usually determined by the action that you're doing. Like if you're just transferring Ether, the limit will be hard coded to 2100. That's right, 21,000. If it's any other more complicated contract code, it will be, the gas limit will be higher. This is automatically determined, right? This is automatically calculated. Rarely, sometimes the calculation will be off and your transaction will fail to go through. This is when some people will tell you to raise the limit. Like raising the limit doesn't mean you have to pay everything. It just means you're willing to spend that much, and whatever is not spent will be refunded to you. All right. So the limit you never change. All right. You never modify yourself. But the price, the gas price, this is what you can control. And this is what to the miners, this is how they determine what transactions that they're going to do, that they're going to take on into the next block and what's not. So you see the transaction fee is calculated by gas used times the gas price. Right. So you see here, I'm not saying gas limit times the gas price, it's gas used. Because the limit, again, is just how much, the maximum that you're willing to pay, you're willing to spend. But it doesn't mean it has to consume all of it, right? And when it doesn't consume all of it, the rest is again refunded to you, right? So gas used is always less than or equal to gas limit, right? So the higher the transaction price, the higher the gas price, the more likely the miner is gonna pick up your transaction. Because if you think about it, if the miner just go off of based on how the highest transaction fees, but then when they're validating their transaction, they also have to replay all the state changes, right? They have to replay their transactions to modify the state. So it means although they're getting a higher transaction fee, they're also devoting more resources on that transaction. So overall, what they look at isn't the transaction fee, but the gas price. Does that any questions about this?
I thought it would be the opposite. I thought they would look at transaction fee because, like, let's say I had a smart contract with like not that much computational like effort.
Yeah.
Even if I put my my price like relatively high, it wouldn't be that much in a transaction fee, right? Because like there's just not that much going on. Versus like if I had just like a medium gas price, then a really high limit, wouldn't it? I mean, wouldn't it end up being more, of course, like if the numbers are right?
Yeah, but then you also have to consider that the Ethereum miners, when they're validating, when they're running your transaction, they have to redo all the computation too. So that costs them resources and money. So although your fee is higher, they're also putting in more resources to run that transaction.
Okay. Yeah, that makes sense.
Yeah. Thanks. So even though your simple transfer has a lower gas used, they also don't take up any computational effort at all. So it's more profitable for them. So the system is set up in a way where the gas price will always be the determining factor. All right. And it's actually a website that tracks it. All right. So it's called ETH gas station. So you can actually you can actually go and I'll send a link in the chat. You can actually go and take a look at it, and I'll share my screen too. So ETH gas station, all right. So so let's not worry about these because Ethereum recently had a change where they changed up. Sorry, they changed up how gas fee is calculated. Watch the brain. They kind of switch up how gas fees are calculated. Sorry, they switch up how transaction fees are calculated, but let's look at the legacy numbers, right? You see that there's like fast, standard, and safe low. And each of them has like an estimated time. That's basically, you know, if you pay, if you set your gas price to 206, then your transaction will most likely be guaranteed to be put into a block in 2 minutes. Be mined in 2 minutes. If it's 168, then it's 5 minutes, you know, 149, 30 minutes. And you can see that it's all determined by the gas price. And yes, these are all very good resources in the chat. And we're not going to go over the new Ethereum, the new kind of transaction fee calculation thing. We're not going to cover that, and it's not super relevant for this class. But usually when you're trying to push through a transaction, let's say you're using a wallet MetaMask or something, they usually have suggested gas fees, and that usually is That's usually, so the automated, so the value that they give you is usually a pretty optimal gas price. So it's not too expensive, but then it doesn't put your transaction on hold forever either. Any questions on gas limit and gas prices and the transaction fees in general? This will be on the test.
How does slippage play into gas prices?
That's more of a, I don't think that has anything to do with gas prices, does it? Slippage.
I can't remember if it's like a liquidity pool thing or.
Yeah, I think that's a DeFi thing.
Okay.
It's a DeFi thing, yeah. Yeah, and we'll talk about DeFi in a future. I forgot which week, but we'll talk about it. Any questions on just calculating transaction fees in Ethereum? So what you have to know for the test roughly is what's in a block, what's in the transaction, how are fees calculated, right? More practical stuff compared to, I'm not going to ask you how a nonce works. Yeah. All right. So let's talk about some Ethereum applications, right? What are, so we kept talking about smart contracts, but then what are some, you know, what are some smart contracts that are kind of out there right now, right? Anyone want to tell us what are some, what, you know, they call it dApps, you know, decentralized applications that you've played with or that you know of? Let's see in the chat. DYDX, Loopring, yes. Dylan, you want to tell everyone what DYDX is?
Yeah, DYDX. Sorry, me and Jared in the same room, so we got some feedback loop. DYDX, they have their own layer 2. It's like a perpetual margin protocol, where essentially you can I think you can short, and then you can get margin trades and leverage trades, and they have a pretty robust system. And it's all on layer 2, which basically means that you don't have to pay transaction fees every single time you want to, you know, open or close a position. They have a pretty complex smart contract that I think I've tried to look through and then didn't understand it at all, so I gave up. I used to use their like I forget what it was called, but it was a feature that they closed down because they really weren't making any money off of it, and it wasn't on the layer 2, so it was a little too complicated to use. But they also have really good visualizations and graphs and technical analyses tools to look at the price and change of Ethereum. So I really like that. And then Loopring is also a layer 2 exchange, and they also have a good mobile wallet that I use sometimes. And they also have like really low transaction fees because they're on layer 2. And they also, you can stake for liquidity rewards if you have any coins that are sitting around not collecting any interest.
Cool. And Loopring, so, and DYDX, which layer 2 are they using, or is it their own solution? Do you know?
Can you say that again?
I'm just asking Dylan, which layer 2 solution is DYDX using? Oh, it's Starkware, okay. Dylan, you're muted, by the way. Dylan's still muted. That's right.
I don't know DYDX's. I'm on their site right now, so let's see if it says anywhere. Products, yes, they use Starkware as well.
Mm-hmm.
So looks like Starkware is pretty dominant.
Mm-hmm. Cool, yeah. So yeah, so mainly right now, I think the hottest thing is the DeFi platforms, right? Things like all the swaps, Uniswap, SushiSwap, PancakeSwap, whatever. But also supply chain management stuff, IBM, they are on Ethereum, I believe. And there's something actually called an Ethereum Enterprise Alliance. So a bunch of big companies are in there, basically trying to develop enterprise solutions on Ethereum. There are also decentralized identity protocols decentralized and immutable storage of information. There are DAOs that we'll talk about in the future, what they are. And I also believe Nicholas briefly said that he had a, yes, OpenSea, the NFT. Well, OpenSea, I wouldn't say it's a decentralized application. It's more of a marketplace for decentralized tokens for NFTs. Yeah, but I believe Nicholas has, right? Nicholas, you have your own kind of NFT thing on Ethereum. You want to talk about it briefly in the last 3 minutes? Is Nicholas here still?
Oh, sorry, was I muted? Can you hear me?
Yeah.
Oh, yeah, I can quickly share it. I have my own like NFT dApp that I built called NF Trees. It's
let's take a
pretty
look.
simple. It's basically just NFTs, and for every NFT that gets minted from our platform, we like take the money and offset carbon with it. So it's just like kind of the first dApp I built because I wanted to learn Solidity. So I built it pretty much over last year, over summer and stuff. And yeah, you guys can check it out. Mint an NF Tree if you want. Go carbon negative, and I don't know, hit me up with any questions or anything if you guys have any. But yeah.
Yeah, so cool. That's pretty cool. Yeah. So NFT trees, you guys can go check it out. Other than that, before we end the class, I have a couple announcements. So first, again, please register for Piazza, enroll. Now, if the link in the syllabus, or sorry, if the link on Blackboard just takes you to like the homepage, then you might have to manually search for ITP-356, and then you're able to enroll. Secondly, and then we have our, we're gonna have 2 TAs. So we already have Jordan. He's already on Piazza helping people. And we're also gonna have another TA that he's probably gonna get, hopefully we can get him by next week. And also another thing, what was the other thing? Oh yeah, so my office hours, right? So my office hours will be after class for 1 hour, Monday and Wednesday. All right, and Jordan and the other TAs, they will post their office hours later on Piazza. Okay, so so most information related to the course, resources, questions, and whatnot, they're all going to be on Piazza. So go ahead and register for that. And homework 0, again, start early because you might run into issues. And aside from that, and also the programming videos, when you get a chance, take a look at them. They will help you immensely. Other than that, I think that's about it. Thanks everyone for coming, and have a good weekend. I'll stick around for a little bit if anyone wants to do office hour stuff. All right, see you guys.
Thank you.
Thanks.
Thanks, Jack.
Thank
See
you.
next
I was gonna say real quickly, if you could help me with, I'm trying to knock out homework 0, but I had some
Yeah.
issues.
Is it the same one that you posted?
Yeah, on Homebrew.
Yeah.
So the place where I got stuck is in like the help section where it says fix. Do you mind if I share my screen real quick?
Sure, you can share. I think I enabled it.
Okay. So let's see. Yeah, so when I would try to enter in this command, I just kept on getting like a bunch of errors.
Oh, I see. Yeah, can you control C?
Control C. Okay.
Yeah, there you go. Now try the commands again.
Okay, dir, and then just press return.
Yeah.
Okay,
You
no
do a
such.
space.
space.
NPDR space. No, so you have, so, okay. Oh, okay. So going all the way back. So brew install NVM, I don't think you did that. So you can't copy and paste stuff like that. You have to do it.
Okay.
Yeah.
All right. So then just try to brew install NVM again. And it says
Oh, you
command.
haven't installed homebrew then.
Okay. So
Wait, let's see. Scroll down.
yeah, I thought I got some sort of verification that installed.
Oh, there's an error. Oh, wait.
Says installation is successful. That's why I'm
Can you close this terminal and open a new one? In typing brew. Interesting. Let's see. One second. Oh. Can you try this command first? Zoom chat, just copy it in. Okay, and then try this line. Second. Okay, now type brew and see what happens. There we go. Now start from brew, install NVM, and then I think you're good to go.
all right. Sounds good. Thank you so much.
Yeah,
All right. Bye.
bye.
Hey, thank you, Professor, for class today. I just wanted to remind you again, because I asked you in the beginning of class about sending homework 0.
Yes.
Okay, cool.
Yeah,
Will that be in the?
Let me give it to you.
Okay, cool. Will that be Google Drive or email?
I'll just send it to you in Zoom.
Okay. Okay, I think I got it. Okay, cool. Got it. So I'll just follow these steps. And what's the due date for this homework?
I think
Or
it's,
does it say on here? Oh, it says here, January 23rd. Okay, cool. Thank you again. Have a good one.
you too.